All right, so thank you everybody for coming to the contributed talks for the BMO week. It's my pleasure to introduce Almaz Butaev, who's going to be speaking to us on BMO extension domains, equivalent definitions, and two theorems of Gehring and Osgood. Thank you, Almaz.
Well, thank you, Ryan. I'd like to thank the organizers for the invitation. Well, I'm going to talk about the BMO extension domain and the two theorems of Gehring and Osgood. This is a joint work with Galia Daphne. Yeah, so that's it. So I don't want to spend much time on defining the BMO space, but I want to bring your attention to the following fact that when we're talking about the BMO space on a cube, everything is clear and unambiguous. We're talking about the functions living on the cube. That's why, first of all, we assume that these functions are integrable on the cube. So when it comes at then the usual definition of the BMO. But when we go to the whole space, when this is the Rn, we have to give up the integrability because, if you assume that the function is BMO in L1, then you're missing all the L infinity functions, I mean, most of them. So, so we're giving up the integrability. We only assume that it's local integrable function and we control the mean oscillation. Well, so, and this is the archetypal example of the BMO function, log x. And what happens to the log x is if we just look at this integrability, what happens to it is if, say, we'll look at the cubes are intervals on R. So if we look at what happens, say, on this interval, and if we look at happens like on that interval, so we see that the variations, because this function is in BMO, the variation from the mean here as well as the, so there is a mean here and the variation here on average are all bounded. That's because log is in BMO. But if we now just look at the average values themselves, right? So on this interval and on that interval, we'll look at the average values. So then here the average value is like this, and there approximately it's like this. And the further this interval will go, the higher the average will become. It's not just the function itself is growing, the averages over unit cubes are growing. And so this is something that we wouldn't like to have. Now, we would like to have some sort of control on the averages. And so what I'm trying to say is that BMO type of functions with a more uniform control of L1 norms, but over unit cubes, say, is if you want to retain this control, you're naturally getting to the BMO space that was introduced by David Goldberg. It's called the little BMO Rn. That space is sometimes called local, sometimes localized, and we prefer the term inhomogeneous BMO space. It consists of functions that are in a big BMO on Rn, and such that apart from the control of the mean oscillation, what you want to control the average values of the function on cubes of size 1 and bigger. All right, so then so this type of questions and this type of spaces are naturally suited to some problems in partial differential equations or some questions in geometry. If you're trying to solve the PDEs on unbounded domains, and so typically what happens if you're solving the AD U equals F, and if AD operator is a differential operator that's completely homogeneous, say a Laplacian, then you can talk about the right-hand side being a BMO. But if this AD is a non-homogeneous operator, if it has lower order derivatives, or it has some constant terms, if the symbol has a constant term, then a natural setting would be to consider the F to be in the little BMO, because big BMO is not suited well for this type of problems. So this is the reasoning from the PDEs, and the little BMO is also well suited for to do the analysis of manifolds, say when you want things to be splittable and localizable. So BMO lacks that. That's why the little BMO is more useful. So, okay, so we figure out what the little BMO in Rn is. So what about the domains? So we can consider the BMO class on any domain, basically. And we can consider the subclasses of a little BMOs with the parameter lambda. So what's a big BMO, first of all? So the big BMO is what it should be. So it's the class of local integrable functions on that set, on that domain omega, such that the mean oscillation is bounded. The thing is, you want to deal with the cubes or balls in that domain that just lie inside the domain. So for example, if this is your domain omega, the cubes that you want to operate with should be the cubes inside the domain. So you don't want to talk about the cubes in Rn that are not properly inside the omega. I mean, you can do it, but then you will be talking about different types of BMOs. Okay, so what about the BMO lambda? Okay, and what is lambda? Before I go there, so in this definition of Goldberg, we fixed the unit cube. That was 1. Instead of this 1, you can choose 10 or 0.1 or 55. The norms will change, the numeric values, but the class BMO will stay the same no matter which constant you fix. So it's not important. So now when it comes to the domains and when we're talking about the little BMOs on the domains, this thing becomes a factor. So that's why we will define like a scale of BMO subspaces, little BMO lambda spaces, as the locally integrable functions such that on cubes of small size, small in the sense of lambda, which is controlling the mean oscillation, and on large cubes, we want to control the averages in addition to that. Yes, so feel free to ask questions if you have any. So this is the definition so far. So this is what we want to look at. So these are the function spaces. Now, so main questions that motivated our research and people who did these things before us were the extension problems. So for big BMO, the question is what BMO extension domain is basically the question what the conditions on omega, on the domain omega, that guarantee that any BMO omega function can be extended to a BMO Rm function. Is there a way to ensure that, assuming some geometric conditions on that? And we can ask the same question for the BMO lambda. So what conditions on omega ensure that the BMO lambda, any BMO lambda function can be extended to a global BMO on Rn? Okay, so the first question's been answered a long time ago. It was Peter Jones who proved the following. So omega is a BMO extension domain if and only if there is constancy such that for all pairs of points x, y in the domain, we have the following relations. So there is one metric, k omega, and there is another metric, j omega, and k is controlled by j. So what are the k's and k? So k and j are here. So this is the definition of k. To measure the distance between x and y in this way, you're taking the curve gamma. This gamma curve connects x and y. So the endpoints of the rectifiable curve inside the omega are x and y's. And then you compute this integral. Oh, it's a line integral over that curve. And then you minimize such a computation, and this is the k omega distance between x and y. Any domain has, so this is a metric on any domain. So the j omega looks even more complicated. So it's a half of the logarithm of the product of two things. So it's the distance between x and y relative to the distance from the x to the boundary and y to the boundary. You multiply them out, you take the square root, and then you take the logarithm of that. Okay, so that may be confusing. So I want to spend some time giving the pictorial description how you compute this thing. So for example, k omega for x and y's, and suppose this is the point x and this is the point y that you have. Suppose we want to figure out, like, get an idea of what is the distance between x and y. So what you do, you connect it with some curve, and so the curve should be like that, so that you stay away from both boundaries as much as you can. Then you do the following. So you look at the ball that's like from this x to the boundary. Okay, so that's like that, right? Now you look at the next ball close to the boundary, like that, right? And you keep doing that. So where you're far away from the boundary, you can increase the ball, okay, like this. And somewhere your ball has to be really small, like that. So once you cover this curve by the balls that sit inside the domain omega, you can just count these balls, and this will give you the number that is more or less, so it's the number of balls covering gamma. And so this number of balls more or less approximates, and gives you the idea of how big k omega is or how small it is. Right, so j omega, so what's the j? So the k omega distance is called the quasi-hyperbolic metric. So that was introduced by Gehring and Osgood, late 70s. And so what they also introduced the distance ratio metric, which is this. And the way you calculate that is simple. Well, it's x and this is y. So you start with the same balls, like this. And yeah, this ball should be like not touching the boundary or just touch the boundary. And after that, what you're doing, you're ignoring the domain completely. You connect this by a straight line, like this. And what you do next is the starting ball, you double it. It's twice as big. This one, you double it. It's twice as big. Then you double again, and then you double again. The moment you intersect, you stop doubling, and then you count the number of balls you have. So it's 1, 2, 3, 4, 5. So that thing is approximately 5 for these x and y, and my very rough computation. So this is the idea behind this k and j. And so that, you see, it gives you a way to figure out like how big k and j are. Just looking at the thing, it's more or less geometric, but there is a better way to give the intuition, to figure out if the omega is good or not. Following the definition of the uniform domain, the omega is called uniform if there are constants a and b such that any pair of points x, y, and that omega can be connected by a rectifiable curve gamma such that this is the arc length. The arc length is less than a multiple of the ambient Euclidean distance. And for any point here, you have that relation. So that as you go along the curve gamma, the distance from the point to the boundary must be increasing relative to the arc length. Okay, so the first condition is called the quasi-convexity. And this condition is called the John condition. Yeah, so pictorially, do I have this? Yeah, so pictorially, that means that if we again talk about this, I'll put this y here and x here. So a good curve, the curve that satisfies these two conditions is the one that lies here. And not only the curve lies in the omega, but also you have a cone. Okay, so let me make my life simpler. Like, first I'll explain what happens. Like if you have x and y here. Okay, so this is x and this is y. A very good curve is this one, is straight segment, and not just the curve, but also a cone that contains it lies inside the omega. The aperture of the cone is that b constant, and because it's a straight segment, the quasi-convexity constant a is 1. You cannot get by using the straight segments if one of the points is here and another is here. Then your curve must be like actually curvy, so you will have a quasi-convexity coefficient greater than 1, and you will need to choose b also very small, because it's really hard to fit this this curve along with the cone around it. Okay, so that's it. So what's the Gehring and Osgood theorems? So what Gehring and Osgood showed, I mean, let's just remind ourselves that Jones proved that the BMO extension domains are the domains where the K metric is majorized by the J metric. And so what Gehring and Osgood showed, first of all, the first result is that if you have any points, x, y, and omega, and they can be joined by a curve that satisfies this uniformity condition, the quasi-convexity and the John condition, then you have this KJ inequality, which by Jones means that then you have BMO extension if you have this situation for all x and y's. And the second theorem of Gehring and Osgood is about the other way around. So suppose that you have KJ inequality. Can you deduce that the domain is uniform? Well, almost. Well, actually, exactly. But the theorem is the following. Suppose that you have 2 points in omega, and you have a geodesic, the one that minimizes that k distance. And if you have the KJ inequality holding for all the points along that geodesic, then the gamma will satisfy the uniformity condition with some A and B that depend only on the C in the hypothesis. So it looks strange and like slightly different. It's from the previous theorem, because here you're asking not just that the KJ satisfied at the endpoints, but they are satisfied along the whole curve. But if you check the proof, that the proof really heavily relies on that, on this assumption. And okay. Now, so Jones and Gehring and Osgood show that omega is a BMO extension domain, if and only if it's essentially uniform. So now, what can we say about the localized inhomogeneous BMO lambda spaces? Right. So the intuition that we talked about at the very beginning, that BMO lambda spaces, they give you an extra control of the averages along the whole space, somehow hints into the direction that these extension domains for these functions must be some sort of local versions of the uniform domains. All right, and which local version? There are at least 2 that we can state. So the first one is mid-90s. The definition of Heron and Koskela is the following. So this is paraphrasing. So given delta, domain omega is called delta locally uniform if you have quasi-convexity and you have the John condition, but they hold only for the points that are close to each other. It's a pretty natural, localized version of the usual uniformity condition. Now, but there was another definition due to Jones himself, and that definition historically appeared even before the Heron and Koskela. In the paper, in Jones' paper in Acta. So where he defines the so-called epsilon delta domain, this is a domain such that for any 2 points that are delta close to each other, you can connect them with a curve. You have quasi-convexity with some epsilon. You have some sort of John condition, but you see, compare this thing to that one. The distance that Jones is using, these are the absolute values. So it's the ambient Euclidean distance. And so the definition of Heron and Koskela, this cone condition, the John condition, is based on the arc length. So these are two different local versions. Although Heron and Koskela in their paper, they say that the Jones epsilon delta domains are the same class of domains that they consider that locally uniform. Unfortunately, they don't cite any result, and it's hard to find the proof of that fact. So it's probably folklore, but we had to reprove it. All right, so assuming that like whatever local definition there is, so what's the local version of the KJ inequality? So let's just recall again Gehring and Osgood. So this is Gehring and Osgood theorems. Look, the first theorem stays valid. I mean, it tells you nothing about the X and Y dependence. So you can, like, if your X and Y are close enough, so if X minus Y is less than delta, then you can still apply Gehring and Osgood, and you can still get the control of this by that, which means that if omega is a delta locally uniform in the sense of Heron and Koskela, then it will satisfy the inequality k less or equal than 1 plus j up to a constant for X and Y close to each other. This is good. The other way around fails though. So if now we have X and Y that are close to each other, if we have these things in mind, and suppose that we have this inequality true, the endpoints, the second theorem of Gehring and Osgood doesn't help us, because the hypothesis of the second theorem is that you have K and J inequality holding for all points along the gamma. And so what can happen is, like, hypothetically at least, you can think of that you have 2 points close to each other, X and Y really close, less than delta, but there is some boundary, some huge piece of the boundary here, all that is the complement, and then the only curve that you have connecting X and Y goes like that, and then you get 2 points, here's U, so here's V, and they are really far away from each other. Okay, so this U and V may get far away. You have no control, and there is no guarantee that you'll get what you want. So is there a way around? And the answer is yes. So that's what our first result is, that there is a modification of the Gehring and Osgood theorem that works for delta local uniform domains. So what you need is the following. So suppose that the gamma is a geodesic through the given points X and Y. Suppose all you have is the KJ inequality for really close points only. And in addition to that, this is a crucial, the endpoints X and Y are close to each other, like even closer than delta. That's delta over 100 C squared. This C is this C. Then you can guarantee that the uniformity conditions hold. Okay, and we have an example that shows that without this extra condition, you cannot guarantee anything. And the example is very simple. You can just look at the infinite strip, pick up 2 points, X here, Y here. The quasi-hyperbolic geodesic is a straight line. For any 2 points that are close to each other, you can fit the cone into the domain, but this domain doesn't, but that infinite gamma will not satisfy the uniformity condition. This is the improvement of the Gehring and Osgood, the variation of Gehring and Osgood that works for in the local setting. So there is another thing about Gehring and Osgood theorem for the epsilon delta domain. So why do we even have to talk about this? So again, if we look back, remember the first theorem of Gehring and Osgood that worked really well when we talked about locally uniform domains in the sense of Heron-Koskela are not that good for the epsilon delta domains, because the assumption here is the gamma satisfies the uniformity condition. The uniformity condition is with respect to the arc length. So it's L, X, Y, Z. And if we want to talk about the epsilon delta domains, this is where the John condition is not with the arc length. This is when you have the distance. And but fortunately, things are not that bad. I mean, the Gehring and Osgood proof doesn't hold because you need to modify it considerably. And so what you get still is the following result. So if you have 2 points X and Y, they close delta away from each other. They can be joined by a curve satisfying the epsilon uniformity condition of Jones. Then you still get the K less or equal than J plus 1 times some constant. And here is a interesting thing, that this constant in this case, it becomes dependent on the dimension. So higher the dimension, bigger the constant is. In the case of Gehring and Osgood theorem 1, there is no dependence on the dimension. And this new phenomena is because of the new definition of the uniformity that we used. Yeah, all that helps us to, so one more thing is that all I'm talking about like is stated in this, in the case of Rn, but it can, without much difficulty, be transferred to the metric measure spaces. Well, there's still some work to be done. But, and so what hints is that this n in the case of the general metric measure spaces with doubling measure will be replaced by the doubling constant, or the geometric doubling constant, if you wish. Yeah, so all that helps us to figure, to establish the following, that if you have omega, that is delta locally uniform, it's Heron-Koskela definition. This is the same as epsilon delta domain. And so this equivalence is a folklore result stated in the theorem. So then we show that this two, all of them, like this and that, both equivalent to the local, to the condition in terms of K and J. And all these equivalences is something that helps us to finally establish that all these things happen if and only if it is a BMO extension domain for the Goldberg's BMO, if that lambda is small enough. Okay, so yeah, that's all then. Thank you so much.
Let's thank the speaker. Are there any questions for Almaz? All right, thank you. Let's welcome the next speaker, Nikos Kalmoukis, who's going to speak to us about holomorphic semigroups and Sarason's characterization of vanishing mean oscillation. Thank you.
Thank you very much. And thanks to the organizers for giving me this opportunity to give this small talk. Yeah, I'm going to speak about this work that in fact is a joint work with Vasilis Vaskalogiannis from the Aristotle University of Thessaloniki. So in the first couple of slides, I'm going to talk about, I mean, general BMO stuff that probably you've heard at least a couple of times today, but I mean, repetition does not help, I guess. And so let's say that we're in the unit circle, T denotes the unit circle. Then the BMO, as you have seen, is this function of the space of L1 functions from the unit circle, such that, okay, first we give this intermediate definition that we have this bracket of f with appendix I is just the mean value of f over I. And the BMO space is a space of functions such that this seminorm, which I denote by star, which is the supremum over the absolute value of f and minus its value on I, the average of all this is uniformly bounded for all intervals. Okay. And I mean, in this talk, we will be particularly interested in the analytic BMO space. So that is functions that are BMO on the boundary, and their Poisson extension inside is an analytic function. And we will denote it by BMO A for analytic. Then we have the corresponding vanishing condition, which says that if this oscillation of the function tends to 0 as the length of the interval becomes smaller and smaller, we say that the function is of vanishing in oscillation. If again the Poisson extension is analytic in the unit disk, we say that it's analytic of vanishing in oscillation, or VMOA for shorts. So, I mean, up until now, I guess we have plenty of motivation to study BMO type spaces, but let me give you my quick motivation, my quick view on the subject. Is that okay? The BMO type spaces play a very important role in function theory in the unit disk in particular, not only but also. So here I will state things about analytic functions, but I mean, almost everything that I say has some real counterpart. So first of all, if HP is the classical Hardy space of analytic functions, so functions analytic in the unit disk, which the restrictions on smaller circles are uniformly integrable, then the dual of the VMOA space, vanishing oscillation, can be identified canonically with the Hardy space H1. The dual of H1 can be identified with BMOA. And then the Sego projection, which maps a function to its analytic completion, is bounded from anything to BMOA. So that's that places the space BMOA in a very central picture in function theory. Then, because in this talk we will also mention a very related space, which is the block space. So in fact, the block space is the space that plays the role of BMOA when we are dealing with the Bergman space theory. So suppose that we have the Bergman space AP in D, which is just analytic functions in the unit disk, which are LP integrable with respect to the Lebesgue measure. Then the same statements hold if we put, instead of the BMOA space, the block space, which is just functions which have this growth on their derivative. And we replace BMOA by the little block space, which are functions so that the derivative has this small o growth near the boundary. Right. Now I would like to come to the theorem that is the motivation behind all this I'm going to talk about today. So we have this theorem of Sarason by 1975, which has the following characterization of functions of vanishing mean oscillation. So Sarason says that if we start with a function in BMOA, then this function is of vanishing mean oscillation if and only if its rotations converge in the BMOA norm to the original function as the angle of the rotation tends to 0. Right? So we rotate the function a little bit, and then we are very close in a BMOA norm to the original function. If this happens, if and only if this happens, the function is of vanishing mean oscillation. Let's keep this in mind. Just to say that just by one reading the proof, he convince himself that the same holds for the block space and the little block space. So if you start with a function in the block space, then it belongs in the little block space if and only if its rotations converge to the original function in the block norm this time, of course. Okay. But then, I mean, if we think about this theorem for a second, we realize that we have introduced an object from another area of mathematics, which is called holomorphic semigroups. So a holomorphic semigroup is a one parameter family of holomorphic self maps of the unit disk. So phi t maps D to itself, such that the first one, F0, is the identity. We have the semigroup law. So the composition of phi t with phi s is a function phi t plus s. And we have some kind of continuity condition that explicitly that phi t converges to the identity uniformly of compact sets as t goes to 0. So the reason why I'm saying this is that, of course, in the theorem of Sarason, the exponentials e to the it times z is a semigroup, a holomorphic semigroup. But we will see this again in a second. For the moment, I would like also to say that there is an equivalent description of holomorphic semigroups as solutions of a Cauchy problem. So if one can look, this is a non-trivial piece of theory, but one can describe holomorphic semigroups as solutions of this initial value problem, where G is some holomorphic function such that the solution, I mean, the G has to be picked in such a way so that the solution of this initial value problem has solutions for all positive times t. So one can prove, it's not trivial, of course, but one can prove that these descriptions are equivalent. The function g, which is uniquely associated to the holomorphic semigroup, is usually called the infinitesimal generator of the semigroup. Now, from the dynamical viewpoint of the semigroups, we can infer that all members of the semigroup have a unique common Denjoy-Wolff point, which is called the Denjoy-Wolff point of the semigroup. And we make a rough distinction, a rough classification of semigroups to the ones that have a Denjoy-Wolff point. I'm sorry, there is a misprint. The Denjoy-Wolff point can belong also to the boundary, so there should be a bound here. So we make this rough distinction to the semigroups such that they have a Denjoy-Wolff point inside the unit disk, which we call elliptic, and the semigroups which have the Denjoy-Wolff point at the boundary, which we call non-elliptic. So notice what I said before, that rotations are form a semigroup, in fact, a group of a holomorphic semigroup, and in fact, it's elliptic semigroup with Denjoy-Wolff point the origin. Now that we have both pieces of information, we have the theory of holomorphic semigroups, we have the characterization of Sarason. It is a natural question, of course, to ask the following. So, are there any other semigroups, holomorphic semigroups, such that we can replace that they can replace the rotation is in Sarason's theorem? So, can we give a characterization? A characterization can be interpreted, of course, in many ways, but what I mean here is in terms of the infinitesimal generator G of semigroups, such that if I put them in Sarason's theorem, the statement is the same. So a function is in BMO is a BMA function is in BMA if and only if f composed to this semigroup converges to f in the norm of BMA as the parameter t of the semigroup goes to 0. And of course, a similar question we can answer for the block space, right? So the problem, as I said, I think it's quite natural, and it has been already investigated by some people. In particular, there are two nice papers of Blasco, Contreras, Diaz Madrigal, Martinez, Papadenikakis, and Siskakis, where they study this problem. So briefly, what they do is the following. They introduce, first of all, the maximal subspace of strong continuity associated to a semigroup, which is so X will be either the BMA or the block space. I use it here for convenience. It's the set of functions such that f composed phi t converges to the function f as the parameter goes to 0. And I mean, it is proved that this space always contains the little version of the space. So I'm referring to either VMI or the little block space, and this is strictly contained in the space X. Now, this result it was by Blasco et al. For the block space, and then by some other argument by Anderson, Jovis, and Smith for the BMI space. So in fact, our main problem now can be formulated as a problem of minimality. So what is the function, the holomorphic semigroups Pt, such that this maximal subspace achieves minimality in this chain of inclusions. And I mean, they prove a characterization of this space as follows. So let semigroup the spaces X and X0 as before, and Blasco et al. Prove that this this maximal subspace can be described as the image of an operator that I will introduce in a second, plus constant functions, intersection with the space itself and the closure. Now, the operator is a quite well-known operator. It's called the generalized Voltaire operator, and in fact is the integral of the function against some symbol. Now, the symbol, of course, depends on the semigroup, and is defined in terms of the infinitesimal generator. So it's not really very important to understand here how the symbol depends on the infinitesimal generator. Just keep in mind that the infinitesimal generator produces a symbol. This symbol produces an operator, and the image of operator describes the maximal subspace of strong continuity. So they have some kind of description of the maximal subspace, and this allows them to give the following two sufficient conditions for the minimality of the maximal subspace. So first, they introduce this vanishing logarithmic block condition, which says that if the reciprocal of the infinitesimal generator has this little growth near the boundary, it's little o of this function, then the maximal subspace of strong continuity for the block space is in fact minimal. It's the little block space. And they have a corresponding condition about the BMO space. So this is a condition which we call vanishing logarithmic mean oscillation condition, and it involves again the integral of the reciprocal of the infinitesimal generator or on Carlson boxes. So I have a picture here for the Carlson box, but I guess most of you know what the Carlson box is. So they have this sufficient condition. Notice that we have one direction only. And this condition, in fact, covers a large class of semigroups. So there are a lot of semigroups that satisfy this condition, and hence this theorem of Sarason holds if we put these semigroups at the place of rotations. But I want to stress here that there are some questions that are left open by the results of Blasco et al. So in fact, it can be verified that there are no non-elliptic semigroups that satisfy either of the two conditions. So if you start with a semigroup which is not elliptic, it always fails to satisfy the condition of Blasco et al., either of the two conditions. So in particular, is there some non-elliptic semigroup which can be used in Sarason's theorem, so such that the maximal subspace is minimal? This is not clear at this point. Another thing is that one can verify by hand quite easily that the vanishing logarithmic mean oscillation condition implies the vanishing logarithmic block condition. But is there an example of a semigroup which satisfies the one but not the other? And the third condition is, of course, maybe the third question is, of course, the most natural one. Are the implications in the theorem that I mentioned of Blasco et al. Reversible? So on this problem, we work with Vasilis, and we have the following theorem, which says that take a semigroup within an infinitesimal generator G. The following are equivalent. The maximal subspace for the BMOA space is the vanishing mean oscillation space. So we have the minimality. And G satisfies the condition vanishing logarithmic mean oscillation. So in fact, we can reverse the implication in the theorem of Blasco et al. But not only this, these are further equivalent to everything else. So to that the maximal subspace on the little blocks, on the block space is the little block space, and that G satisfies the vanishing logarithmic block condition. So everything turns out to be equivalent. And maybe one could guess that from the theorem of Blasco that this A and B would be equivalent and C and D would be also equivalent, but it's quite impressive. I think that quite interesting that all of the four conditions are equivalent. So we can answer to our previous questions. In particular, there exist no non-elliptic semigroups that achieve minimality of the maximal subspace, and the conditions VLMO and VLB are equivalent for semigroups. So how much time do I have? Do I have like 5 minutes?
Maybe like 7 minutes.
Great. So that's the main theorem. I just want to give some hints about how one would go about proving this thing. I will start maybe with the fact that B and D are equivalent, which seems a bit counterintuitive. It seems a bit counterintuitive until you bring in mind this theorem of Pomerenke, which says that for a univalent function, being in the little block space is equivalent to being in the VMOA space. So of course, this theorem does not say anything in our case, but with Vasilis, we managed to prove a weighted version of this result, which is relevant to our problem. So suppose we have a positive C1 function in the unit disk, a weight function, which satisfies the following regularity condition. So the modulus of the gradient times 1 minus z, modulus of z squared is controlled by a constant times the weight, and this constant has to be strictly smaller than 1. So if we have such a weight, then the following are equivalent for a univalent function. The derivative has this growth on, near the boundary, and we have this weighted BMO type condition. Again, SI here is a Carlson box. And then this together with the fact, this together with the fact that this symbol gamma that is induced by the semigroup is univalent. If you write everything down, you can see that it gives you the equivalence between the VLB and VLMO conditions, where of course omega in this case is this logarithmic weight. So that is that. And then, of course, we have to talk about the other implications. So let me, just for convenience, let me introduce this BMOA log space, weighted BMOA space, which is a space of functions such that we have, I mean, this quantity that defines BMOA functions weighted by this logarithm of the reciprocal of the length of the interval squared. And of course, the corresponding vanishing condition, so as the length of the interval goes to 0, this quantity becomes 0, defines the vanishing mean oscillation logarithm. space. Then we have the following lemma, which says take a function g which is in the space BMOA, but it's not in the vanishing logarithmic vanishing MOA space. Then we can construct the function f in BMOA such that the image of f under the operator TG, this is generalized Voltaire operator that I defined before, is a BMOA function, but it's not a VMOA function. So that's the central technical, let's say, lemma in our construction that allows us to prove our results. And I will show you why, because suppose we want to prove, if you remember, that if the maximal subspace is the VMOA space, then gamma must satisfy this vanishing mean oscillation, logarithmic vanishing mean oscillation condition, which is equivalent to say that gamma belongs to this VMOA log space. So suppose that this does not happen. So gamma is not in this space, but yet we have this this equality. Then it can be proven that when phi is elliptic, then gamma is necessarily a VMOA function. Therefore, we can apply our lemma for the function gamma, and we can construct a function f as in the lemma. Then, immediately, T gamma of f is in the maximal subspace of strong continuity by the theorem of Butaev, which says that this space is just the image of T gamma practically, but by construction is not in the VMOA space. And that concludes the proof, because we constructed an element inside this difference. We have reached a contradiction. So this takes care of the elliptic case. Well, the non-elliptic case is a bit more tricky, but not that much. It requires some more arguments, but this is just to give you an idea of the proof. Yeah, it requires next time. So here I have some references, in particular the two works of Blasco et al., the work of Anderson, Jovovich, and Smith, and our preprint on the subject. Thank you very much.
Let's thank the speaker. Thank you very much. Does anyone have any questions?